Welcome to the first Thursday Tech Talk, everybody. And I'd particularly like to thank the folks coming in by Blue Jeans. There's 7. So what would be better than people coming in to hear biostatistical talk over the internet? So I think this is fabulous. So I just wanted to introduce this whole series, which I think is very important. A couple of months ago, I guess, Claudine pointed out to me that she really missed having the technical lectures, the biostatistical, epidemiologic, or IT technical lectures that were a big part of the Innovative Discovery Series. Because this Innovative Discovery Series got bigger and broader, we realized, of course, that we had to appeal to a wider audience, so they became less technical, which is fine. But there's a place for both, isn't there? So I think this is really very, very important. And could we do better for the first of these series than to have the head of biostatistics for all of Christiana, Paul Kolm, and now our fearless leader who reintroduced the technical talks, Claudine, is going to introduce Paul.
Thank you, Peter. This is very formal. So we are really delighted to have our own Paul Kolm today to give a talk and on the time series, and that's something that I think we are very interested in as a group, and because of our electronic health records, the time series techniques is really something that we want to develop, understand, and use. Before I introduce him, let me mention some housekeeping issues. First, make sure you sign in. Please RSVP so that we can better prepare for the next session. Online participants, please keep the mics muted unless asking a question and keep the video turned off. Use the chat feature in Blue Jeans if you have technical questions. And make sure you subscribe to the series to learn about upcoming tech talks. You must subscribe separately from the Innovative Discovery series. Next month, we'll have our colleague from Nemours, Jefferson Hossein, who is going to talk to us about growth trajectories leading to early childhood obesity. And all the schedule of the Tech Talk is on the ACCEL website, and all the previous presentations are on our website also, DE-CTR.org. So Paul, we've known him for a long time. Paul is Professor of Medicine at Thomas Jefferson Medical College in Philadelphia, and also the Director of Biostatistics at Christiana Care. He has a PhD in psychology and measurements from University of Nebraska-Lincoln, and from there had a very distinguished academic career. He started his career as assistant professor in statistics at Southern Illinois University of Medicine in Springfield, Illinois, then worked as Director of Biostatistics in the Eastern Virginia Medical School in Norfolk, Virginia, and then as Director of Research at the Naval Medical Center in Portsmouth, Virginia. Then in 2002, he moved to Atlanta, where he was Associate Professor of Medicine at Emory University and Director of Biostatistics at the Emory Center of Outcomes Research, led by Dr. Weintraub in the cardiology division. He has taught multiple courses in biostatistics from basic level to very advanced level, has a very long list of publications, has been funded as a co-investigator biostatistician on multiple grants, and really has been instrumental in the success of many, many of our grants. So thank you, Paul, and I can't wait.
When I started to put this together and sort of work through how I would go through building a time series model, before I even got to the first model, I had 39 slides. So I realized I'd have to do something different here. I'd never get through. So I'm going to go through sort of the basics of time series, developing time series model. There's a number of things in here that if you'll just kind of take my word for it for now, that would be great, and we can get through it. Because I have homework for you. And so I have like everybody else who has way too much to say, they put a supplement in their research article. So I have a time series supplement, and if you would like a copy of that, then you can just email me. I provided the very last slide here on that, but it has some of the detail that I'm going to have to skip over. So the outline here, I'm going to do univariate time series models, and then we're going to talk about how you apply this to do interrupted time series analysis. Then multivariate time series, and the two concepts here we're going to talk about are cross-correlation and Granger causality. Okay, so here is probably arguably the most recognizable time series in the world, although I suspect that many people who sort of use this have no idea what a time series is, as you know, investors who invest in the stock market. But anyway, that's a picture of a time series. Observations over time. So more formally, we have observations at different time points. These typically the interval between time points is a constant, but it doesn't have to be. We can have variable time between measurements. It's also comprised of usually aggregated data. So in other words, if you have the mean of something over a period of time, but again, it doesn't have to be. It might be counts, like in medicine, we might have the number of infections, per month. Hospital over a ICU over a. The most important component, though, of the time series, or probably the most salient one that we need to understand, is the idea of serial correlation or autocorrelation. And this is the idea that present values are dependent or correlated with past values. And typically that the values closer in time are more highly correlated than the values further apart in time. Makes sense. In time series jargon, these are called shocks. I'm not sure why they call them shocks, but it's like the past value in the time series comes up in shocks the present value. That was probably economists, who predicted, a jump in the stock market, but unfortunately it, crashed 500 points, so maybe they were shocked. So here's what I mean by autocorrelation or serial correlation. So if I have measurements here, I have a baseline measurement at time 0, and then I've followed individuals or whatever for 12 months after that, and I have data, some sort of data each month. So I can correlate time 0 with time 1, time 1 with time 2, time 3 with time 3, and all the way down. Then I correlate time 0 with time 2, 1 with 3, 2 with 4, 0 with 3, and so on. So I can get all of those correlations. Okay? And if you have a long time series, then if you plot these correlations, then they would look something like this. And the lags here are the time 1 versus time 2, time 1 versus time 3, and so on. And it would look something like this, where you get fairly high correlations for measurements closer in time, or in other words, the lags that are closer together, and then they die out over time.
So what's ACF? What's the?
This is the autocorrelation function. These are the correlations, and these are the lags.
So that means that further on out it becomes more?
Knew someone was going to ask that question. So we go through this. Okay, time 0 with time 1, that might be a high correlation. Time 1 with time 2, okay, those are all closer together. As we keep correlating here, time 0 with time 2, get time 0 with time 3, time 0 with time 7, the correlation gets smaller and smaller. So when you come back and calculate those, then you get this sinusoidal kind of thing, because you're correlating the lags. Okay. Let me push on and we'll see. Okay. So the other time series components that we need to talk about are trends. Okay, so that's the tendency of a series to increase or decrease. Drift, you can think of that as a non-significant trend. The series is drifting up or down. We can have a cyclical component. That's an aperiodic oscillation around the trend. In other words, it's not a systematic kind of cycle, but there is some sort of cycle in there. And that's in contrast to what we call a seasonal trend, where you have a periodic or a regular increase or decrease. So here, if you think of seasonality, if you think of like if we have a time series of flu epidemics, there will be certain times of the year. Or if you're in sales, you'll see a trend probably related to Christmas. And then finally, we have the random error or the random noise, just like we do in regular regression. And we'll talk about that in some length here, what we mean by white noise. I might say that, I meant to say at the beginning, that the terminology and the concepts in time series can be kind of confusing. It's not really like regression, although in some sense it kind of looks like that. It's not as easy to understand as regular regression, linear regression, and logistic. Okay, so why would we want to analyze data as time series? Well, it's a practical way to do it, analyze the data. If you have a long series, you have a long period of time where you've measured, you have some measurements, and that these are likely correlated. We might have an interest in looking at trends or seasonality. And then we can use the time series as a quasi-experimental design to assess the impact of an intervention. Or we can compare two or more time series to assess what I call causality. That's what I'm going to talk about mostly here. And then finally, the other use of time series is to forecast future values, which is primarily in the domain of econometrics. I've never seen forecasting in medical literature. Even if I did, I wouldn't believe it. Anyway, that's kind of sort of the three areas of, or the three things that you would want to use a time series, build a time series model for. Okay, so we'll get into a little bit of the tech here. So here we have a linear process model. Okay, that's just another name for time series. That's the thing that different groups call the same thing by different names, so it gets kind of confusing. But so anyway, what we have for a series here, we have the lag time t, time t minus 1, t minus 2, and you can see that there's a coefficient, a phi coefficient here at each one, and then we have our error, our random error. So that looks kind of like a regression equation, but it's not exactly a regression equation.
So what is the y here? So dependent variable.
These are the measurements at each point in the time series. That's what y of sub t is. Okay, and then this is the measurement before time t, 1 before time t. This is the measurement 2 back and 3 back and so on. Lag. Okay. Now,
so that actually looks like fairly simple regression.
Yes.
Except that your times, your y is the y minus t minus 1 minus 2.
Right. You can see here that in contrast to regression, where the y's here are all lag times, whereas in the usual regression, these are like different variables, different risk factors.
In a simple sentence is that current is the past function. Today is our previous function, which means today is decided by yesterday, the day before yesterday, and so on.
Now, I'm not going to go through this, but you can, go based on this equation here. It turns out that the coefficient here, phi at time 1, if you raise that to the jth power, then that's the autocorrelation between the value at time t and the value at time t minus j. So let me give you an example of what I mean here. So if, remember in my series I had times 0 through 1 through 12. So obviously, if you correlate something with itself, you get a correlation of 1 that's perfectly correlated. So let's say that the correlation between my time 1 and my time 0 is 0.93. Okay. So at the next lag, in other words, 0 or the lag time of 2 versus my time 0, then that correlation is 0.93 squared, and so on. At this J here. And so you can see that what's happening here as the lags get further and further apart, the correlations become smaller and smaller.
If it doesn't change. If the correlation doesn't change, like he has 0.93.
Oh, right. That could be, that could be anything. It could be you start out at 0.67.
No, I think you're saying are you assuming all the autocorrelations are the same? So the correlation between time 1 and 2, is that going to be the same as the correlation between time 2 and time 3?
Yeah.
Right.
Yeah.
But the time interval need to be exactly the same then, right? Isn't it? The time intervals.
No.
Right.
But why is the correlation between 0 and 1 the same as the correlation between 1 and 2, or 4 and 5?
No, it wouldn't necessarily have to be.
But for this to be true, I see this is a linear process.
Yeah.
If you have a nonlinear process, it wouldn't be true.
So, and then you can see that this is actually a fairly stringent condition here. This is what we call first order autoregressive. Because it's like probably in real life, not too many things are going to actually follow that that pattern, but that's what's meant by autoregressive, first order autoregressive. Okay. Okay. And you need to talk about expectations. Okay, expectations, or that's just a statistical term for looking at the expectation of some statistic. So, like when we talk about an expectation of the normal distribution, we're talking. So, the expectation here of the series is the mean of the series. In other words, if you take all of the values in your series and find the mean, that's the mean. This is then the covariance between the value at time t and the value at time t minus j. So that's the covariance, and the assumption here is that that's not equal to 0. In other words, we have autocorrelation in our time series. Okay, if we have, and for our error, our random error in the model, if the expectation of that, if the mean of that is 0, the covariance is 0, and we have some finite variance, then we have what we call white noise. Mean of 0, no correlations between time t and t minus j, but there's some variability in it. We have white noise, and then if the y at time t and time t minus j is a function of some value gamma, then that means that the series is stationary. In other words, we have the same mean and autocovariance across the whole series. So those are a few important things to keep in mind as we. Okay, building the time series model. How do we do that? So if the time series, the original time series, is not white noise, then we need to pass it through the series through the components, or pass the components of it through series. By components, I mean the autocorrelation, the trends, and so on. That's what I mean by the components going through the filters. So in other words, we're going to need to, in a sense, take away the autocorrelation. We're going to need to take out the trend. We're going to need to take out seasonality. Why do we do that? Well, the assumption is that the model that generated this time series is stochastic. If you have a stochastic process, that means that there's variability with at each point. Okay? So what we want to do is we want to take out the error component of that so we can work with the model that, or the actually the process that generated this particular series.
But why would we want to take out the trend? I mean, isn't it what we want to look at?
Well, no, if you leave the trend in, then that's going to confound the analyses that you do down the road. So if we do that, in other words, because we don't want the error in there, we have to have a model that's free of the error, that's stationary. It doesn't have any trend, doesn't have any autocorrelation. And then we can do our interesting analyses of looking at the impact of an intervention or compare two or more series. Like I say, okay. The important assumption, just like it is in linear regression, that the residuals, the difference between the observed time series and the predicted time series, are normally distributed. If the original series has no trend, no autocorrelation, then and the random error is white noise, then the series is just random fluctuation off the mean. There's nothing else we would need to do with it. Okay. In my presentations, if you've been to mine before, you know that I usually have one slide that's kind of the important slide. The serial, well, this is the next one is it.
Okay.
If you remember nothing else,
needs to wake up.
remember this one, okay? Box is actually the guru of time series, the Box and Jenkins method for doing time series. So this is never more true than when you do time series analysis. But it's also true if you do linear logistic regression as well. Okay. So here's the time series. We'll get to the interesting stuff now. Get through this. So here's the data that we have from the Bridges project, or one piece of the data, and this is readmission, 30-day readmission rates. And so what I have here is the average readmission rate for each month over the data that we have from January of 2010 to September of 2015. So I have almost 6 years of data. I've got 69 time points. So that's what this is my series. Okay? So the first thing you do in building the model is you obviously plot the time series and you look at it. Okay, so what do you see? Model. Is there anything that you can say about it just by looking at it?
Increasing variance. There's some recurring dips.
Well, yeah.
Big dips.
Are there?
Kind of, sort of.
Okay, you can't really tell much just by looking at this.
There doesn't seem to be a trend.
Looks like white noise to me.
Okay, that would be the first best guess, because we don't really see any trend in here. It doesn't look like there's any consistent oscillation, seasonality. It's kind of bouncing up and down. We got a couple big spikes here, but so anyway, so after that, then what we want to do is we want to take a look and see if we can kind of figure out what might be happening in our series. So we do, so we apply some smoothing method to see if we can see a trend or oscillation or whatever. So there's all kinds of different smoothing techniques that we use. We can use for this. These are all linear. Then we can use nonlinear and exponential, double exponential, and so on. There's all kinds of smoothers we can use. So which one you pick and how you define it makes a big difference.
Paul, is smoothing the same as filtering?
Yes. You can look at it that way. Okay, so here's my series, and so what I'm going to do is I'm going to apply a couple of moving average smoothers here. And so my first moving average looks like this. And what I mean by moving average is you take at any point on the series here, you take a certain number of observations prior to that, a certain number of observations after that, and you average those together, and that becomes your point. Then you go to the next point in the next observation in the series, and you do the same thing. So the red line here is taking 2 observations prior, 3 observations after any particular point here, including the average and then replotting. That's what we mean by a moving average.
And do you, I mean, is it, how do you determine how many observations you take?
Well, sort of, you ever heard the term, you use statistics to lie? I don't really believe that. Kind of borrowing from the NRA, statistics don't lie, people do. So here's my next smoothing where I've taken 20 points prior and 20 points after. And you can see what's happening here, that I'm smoothing it out. And if I take a big enough span here, I'll get basically a horizontal line. So it depends on the span you take what this is going to look like.
Can I add something based on your question? You can actually analyze the ACF, which was in one of the previous slides, and that can tell you whether moving average is a good method and how far you can go back and forth, whether 3 or 20 or 5 makes sense. That actually tells you whether you can use moving average or not.
There's criteria for that?
Yes.
Okay.
So you look at the shape of the ACF, and then that tells you, combined with another graph, but those 2 tell you whether you can do this and how much you can go back and forth, whether it's gaps of 3, gaps of 10.
Yeah, I actually have a graph of those. Okay. So let me do another one here. My first one here, I'm going to use a polynomial smoother, a fractional polynomial smoother. So that was pretty horizontal to me. So maybe my first guess of it being white noise to start with was bad. And then here's a median spline. Span of my, in this case, is 15. So again, it kind of depends on the spans that you use for each of these smoothers. But you can see that here that I've got some oscillation, although it doesn't necessarily look like it's very seasonal. But anyway, so that may give me some idea of what I have here so far. My initial judgment that it might be white noise. That might be the case. Okay, so now we're going to start building our model, what we call an ARIMA model, or an autoregressive integrated moving average. What does that mean? Well, autoregressive, we've already talked about that. Moving average, we've kind of discussed that a little bit, what that means. Integrated means differencing. I'm not sure whether they use integrated and differencing, but basically it might be that we have to difference our series to achieve white noise. And what do we mean by that? Well, you take value of time t and you subtract the previous value from that, and that's your new point on your series. Okay? So we call that first order differencing. We can also do second order differencing. We take t and then t minus 2. Those. So that's what's meant by differencing. If we don't require any differencing, then our model is just autoregressive moving average. And so the notation that you'll see in books and so on, textbooks, is that we write our model like this, where we have ARIMA and then we have subscripts P, D, and Q. And P is the autoregressive component, D is the differencing component, and Q is the moving average component. So if we have an ARIMA 111, that means we have a first autoregressive, first order difference, and a first order moving average model. We can then also, it may be that we need to add seasonality. So that's just sort of the same idea here, except we use capital letters here to indicate the seasonality and subscripted with S. So in this case, if we have monthly data like I do, our seasonality coefficient is 12. If you have quarterly data, it's 4. If you have weekly data, it'd be 52. Okay, one of the things, statistical significance. In time series, the statistical significance is dependent on the number of time points you have, not the number of subjects that are involved in that time series. So for example, in my readmission time series, there's about 100 to 110 patients at each month that make up the mean, but I can't use that for statistical significance. It's the number of time points. And then the same thing is true when we look at the model parameters, tests for white noise, and so on. It's, parameters are coefficient divided by the standard error, but the standard error here is based on the number of time points, not the number of subjects. Unfortunately, in contrast to like linear regression, in particular logistic regression, there isn't any statistical comparison between models, but we can make comparisons based on the information criteria. Kite's Bayesian, and that's in the supplement I have, a little better discussion of that. So for now, if you'll just believe me when I say that when you look at these, smaller, better.
But what's your hypothesis? I mean, test significance of what?
Well, the significance of correlations and the significance of parameters of the model. Here we're trying to find out which model is better. But like in logistic regression, -2 times the difference in log likelihoods, that's distributed as a chi-square. Here we don't have anything that's distributed. There's no statistical test that we can make between two different models. But we can use the information criteria to help make a decision on which model is better.
Statistical significance is about whether the particular type of filter you apply fits, yeah, and not the validity of the data. Because if you have a time series, 10 people that are aggregated for each time point versus 1,000 people, you're not saying anything about the error proneness of those data, right? Yeah, right. You're just testing the fit to the data you have.
Yeah.
Yeah. Right.
Okay. So here, as Muge mentioned, here's my autocorrelation function. Here's my partial autocorrelation function. And so you can see that for the autocorrelation function for my data, for my readmission data, it doesn't really look like there's any significance here. So that kind of, again, tends to indicate that we may have. On the other hand, the partial autocorrelations, there are some significant correlations there. Partial autocorrelations are just like when you talk about partialing variance out of two correlations, or you take two correlations, you take two variables, correlate them together, and you partial out a third variable. Well, that's what this is. In other words, the correlation here is adjusted for all the other correlations in the series.
So how do you know that it's not significant, the autocorrelation?
Well, remember that I have 69 time points. So if I can create a 95% confidence limit, which is 2, that's the normal distribution, 2 standard deviations, and divide that by the square root of 69, it turns out to be about 0.24. So significant correlations now in my time series is going to be either plus or minus 0.24, and that's so looking at that, and so here the partial autocorrelations, there are some here that are in some of the later lags are significant, so I'm not quite exactly sure what to make of that, since none of these look like they're, as far as helping me decide what kind of model.
Is this after differencing?
No, No, this is just
Before.
This is just before. This is the original series. So I'm going to just start, developing some models and then seeing how they compare. So my first model, and where you would always want to start, is just with no autocorrelation, no differencing, and no moving average. That's just the original series as is. And so my coefficient here for the constant, it turns out that if you don't do anything, then this is just the mean of the series. Once you start adding more autocorrelation or differencing, then this constant is no longer the mean. Its mean would be a function of the constant plus whatever else you put in the model. The sigma here is the standard error of my white noise. Okay. So now I want to check, and I want to see if my original series, as his series, is white noise, and if the residuals are normally distributed. Okay. So there's a test I can do for that. It's called the Bartlett test. Again, this is in the supplement, so I'm not going to. But basically, what we have here is you have diagonal line and 95% confidence intervals, and if your points sort of fall within that, and the statistic is not significant, then you can conclude that you. And so, in my original series, without doing anything to it, it sort of looks like that's what the case is. And then my residuals, I can just do a normal quantile check of that, and so you can see that my residuals are pretty normally distributed here, except for a couple of. So this would lead me to conclude that maybe my original series, without differencing, without it's correlated or anything, is already white noise. Then let me do another one. I'll add in a autocorrelation component to do the same thing. So there are my parameters for that, my test for white noise, my test for normality of residuals. And so you can see that here it's a little better when I put in autocorrelation. The test for white noise. Well, I could keep going here, but obviously we don't have time to go through every model I checked. So here's just a selection of some of the models I looked at. So the degrees of freedom relates to the number of parameters. So what you want is the simplest model that is white noise, and the residuals are normally distributed. It turns out that that's the case for all of these. So in other words, you can see here I have 6, 7 models that are all, in a sense, valid. So which one do you choose? Well, we could use our information criteria here, and you can see that these first 6 here, the information criteria are fairly similar. There's not much difference there. But when I add in differencing and put in a seasonal component, it drops quite a bit. So just based on that, I would want to go with this model. Now, whether that's right or not, the information criteria doesn't tell you anything about that. It doesn't tell you how good the model is, how useful it is. It just tells you that, in comparison to these other models here, it has the best combination of complexity complexity and parameters in the model. So I wouldn't have to, but I'm gonna go with this one, just for illustration purposes. So this is what the parameters are, and this is my test for white noise. It's still not significant, and my residuals look pretty good. I've actually taken care of some of the outliers. And then if I plot this, my stationary model, this is what it looks like. So you can see I've taken out whatever, if there was any trend, any autocorrelation. this, you might say, okay, well, what's this here? Well, I have a seasonal component, and I difference that, so that's why you're see that horizontal line there for the first year. If I hadn't put in a seasonal component, you wouldn't, you know. Okay, so keep that model in mind. Remember this.
It seems like the variation gets a little bigger over time. Is that my imagination, or?
Right, it does, yeah.
Okay.
It looks like it. But you know, based on the test for white noise, it's and the normality of my residuals. This is the model that I would. This is what the stationary model would look like with all this stuff. Okay. We want to do one more here, hopefully. Get through this quickly. Okay, so this is the Elixhauser comorbidities. Yeah.
Before you move on from that other example, how do you actually, and what's the inference that you make from it? I mean, especially on the previous slide where you had the coefficients, how do I interpret those? What do those mean?
Well, the thing is, we're not particularly interested in the model itself. What we want to build is a model that we're kind of okay with. It's might be really good. It's what we want to do with that model that really matters.
Okay, so that's where you're building up with this?
Yeah.
Okay.
Right. So it's like, and you can see here, since I difference it, you know, my constant is no longer near the mean. In fact, as you difference it, this constant here would tend to 0. You're flattening it out. So in one sense, I mean, the only thing that these are useful for is getting the values off that. So now, then I'm ready to do something, you know, with this model.
But the parameters you see in parentheses are meaningful from a clinical perspective. You could interpret those, right? Not necessarily the coefficients, but you could look at this. If this is the model that you pick, you could say, okay, I can see what this implies. You're saying that whatever the measurement is highly correlated with the measurement right before it, because you have this one for the autoregression piece, right? And the one in the middle tells you that there was some concern about that the time series was not stationary. That's why you needed to take the difference, because otherwise it would be 0. And then you see the seasonality of 12, which tells you what happens this January might show some seasonality with what happened last January. So you can, in terms of the readmissions example, like you can look at those and interpret those, not necessarily the coefficients, but the parameters mean something.
But that would be, that's kind of a general description of what it means, and whether or not that's useful information may or may not be useful to.
But the seasonality of 12 is, I think, interesting because it's collected monthly. So you're saying that there's a yearly seasonality for readmissions, which is not something you would necessarily see if you think about readmissions or 30-day readmissions.
Okay. Okay. So I'm going to quickly build another model here of comorbidities, and this is the total count. In other words, this is the average comorbidity per month for PCI patients. Okay, now we look at this. What would we say? Just by looking at this, there's a trend. There's a trend here, isn't there? It certainly looks like it. So here's the mean of the series. Here is a polynomial smooth, and here's a median spline smooth. So clearly, there's a trend. So I'm going to go through the same process, build the model. I start with nothing here as far as autocorrelation, differencing, and so on. When I do my test for white noise, you can clearly see that the original series is not white noise, which would have expected anyway since we saw a trend. Residuals are fairly normally distributed, although we've got a couple of big outliers there. So here's the models that I looked at. You can see that These two here, where I've differenced it, are a fairly large drop from the information criteria of the other ones. So in this case, it would be pretty clear that I would need to difference the series in order to get to stationarity or white noise. I'm going to go with this one. It's actually fairly close. I could really take either one of these. This one has one less parameter, so I'll go with this one. My coefficients, and here's what the stationary series looks like. Now, we get to the part. I'm going to go back to my first readmission series, and I want to do an interrupted time series analysis now. And so in the Bridges data, we have the introduction of an intervention, care management. So when we look at time series, when we look at an intervention and time series, this is sort of the typical way that it's done. So you have a before and after, and then you look at the difference between the two at the intervention point, and you want to see if there's any effect here. Now, you'll probably never see anything in reality that looks like that, but that's what actually looking at regression lines before and after are the typical way that people analyze this data. Called segmented regression of the time series. I'm not going to do that, but that's what we need. Is you can by using the ARIMA model, we can then determine whether our intervention had an effect and whether it was gradual or permanent, gradual or temporary, abrupt and permanent, abrupt and temporary. For the Bridges project, the hypothesis would be that we'd hope that our intervention would decrease readmissions, but we would expect that to be gradual, permanent. You wouldn't, when you have a process like introducing care management into something, you're not going to get an abrupt change. But we might see a change over time. So that would be our hypothesis. So here's the series again, and I put in where the intervention occurred or began in April of 2013. This is 1 year later. So what we want to see is if there was any effect of the intervention on readmission rates. So here's, remember the model, the stationary model? So I'm going to do another model, except I'm going to use that stationary model, but I'm going to introduce the Bridges intervention model. So now I have two coefficients here, the Bridges coefficient and my constant in the model. I have both good news and bad news. Good news is that this coefficient is negative, so that means that my readmission rate is decreasing. Bad news is it's not statistically significant. Okay. But I'm going to go ahead and show you what we could do with this anyway, even though it's not statistically significant. Using these two coefficients, and we can calculate what the effect the Bridges program had on the readmission rate. This is what it looks like. Remember, I posited a gradual, permanent effect. But before you get too excited about this, just, the scale here goes from -0.23 to -0.29, so it's not. But you can see here that it decreases, and then it reaches an asymptotic level here. So when you have a gradual, permanent effect of the intervention, it'll look. And this is not plotting the actual readmission rates at that much. It's plotting the effect of the intervention.
But what's a unit? The Bridges effect. What does it mean?
Months. Remember, I have it's in months.
And then the Y scale.
No, on the Y.
This is the effect. So this would be like about 0.25% of readmission rate if I've expressed my readmission rates, which I did as percentages, then talking about a 0.25% reduction in readmission rates over 2 years of data that I have. go to, let me skip that. This is just, you can look through this later on. So what we want to do is we want to correlate two time series. So I've got two time series now. I've got my readmission rate and I've got my comorbidity time series. So I'm going to take those two stationary series and I'm going to cross-correlate them. This is how you get the correlations. It's basically just like any correlation. It's the covariance divided by the standard error here, which is the square root of the product of the variances. So when I do this, then I should get, if I say that y or x leads y, in other words, I'm saying that x is causing y. This is related to the idea of causality, that one of the elements of causality is that the cause has to precede the effect. You can't have it the other way around. So when I plot my correlations, then on the positive side, for positive k, I should get some peaks in the correlation. On the negative side, I would get non-significant correlations. So, of course, what I have suggested here is that the comorbidity level is having the effect on readmissions. So when I plot it here, then I would expect non-significant correlations for the lags, in other words, on the negative side or left side, and I would expect some significant correlations for the leads. And then this is my 95% interval, and I get this really pretty picture. I already kind of knew that we have non-significant correlations here, but we have some significant correlations over here, which means that the comorbidity count is leading readmissions. Then one other thing I can do here, and in the same vein, but in a different little different methodology, is to look at what we call Granger Causality. So it's the same kind of idea. Do past x values contain useful information to predict the y value? So we can do it. In other words, if we add to our linear process model here the lags on the x time series, then do those add to the prediction of y? So basically what we're asking is y a function of x, or is x a function of y? So there's only really there's four possibilities, but only two of them make sense. So if y equals x, that is, in other words, that's significant, but x is not equal to y, in other words, x doesn't y not equal to x here, then we say that x Granger causes y. Is what we say. If neither one are significant, then we can conclude that they're not really related. If both of them turn out to be significant, then we really don't know anything more than we did before. That shouldn't really happen, but if it does, it's like, you know. The other thing, and this probably my thing, this should be y Granger causes x. That might be meaningful in some contexts, but depending on what x and y are, that might not make any sense. In other words, if we say that readmission rates Granger cause comorbidities, then that doesn't really make any sense, because our comorbidity data was collected before we knew what the readmission rate was. It's really these first two that. So my hypothesis is that 30-day readmissions are a function of comorbidity count. Here are my results. For lags 3 through 13, I find that the admission as a function of comorbidity count is statistically significant, but my comorbidity count as a function of admission not significant. So I can say that morbidity count is Granger causing admission rate. I've just done this for two variables here, but we can extend this for any number of covariates. We'd have a truly multivariate kind of analysis here where we could look at the Granger causality of all of these in relationship to admission.
But wouldn't you need to do another time series for each of these covariates?
Yes. No, this is another tech talk.
Oh.
Okay, but we're out of time, so thank you.
Yes, this fall was my first time teaching. Yes, I did actually.
Attach it and send it back. Okay. I'm sure there are no questions. So one thing I might say is that in the supplement, I have a bunch of references in there. I grouped them in two groups. First set is the theory and methods, which you may or may not be interested in. And then the second set is some examples of time series analysis that have been used in actual publications in the medical, generally the medical field. They're kind of hard to come by because you don't see too many of those. And the references that I've given don't always use the ARIMA model. You can get kind of a flavor of how different, how there are different time series methods, and then also what people call time series that aren't exactly.
So, looking at the data and the Granger causality, if I got this right, you're finding that comorbidity Granger causes a readmission, which means it has to occur earlier. It's occurring earlier. But I don't quite understand because I didn't see any pattern at all to the readmission. So how can something Granger cause it if it's not varying time? Am I missing? I know I'm missing something, but maybe you can explain it.
Well, it doesn't necessarily have to vary over time.
Huh.
It's just whether there's a correlation between, the two series. So there was variability in the comorbidity one. There was a trend there, but there wasn't really a trend in but that doesn't necessarily mean that they're not related or not.
It was what you'd expect to see at some level. Is if comorbidity is going up, then there'd be a lag, and then readmission would start to go up. I mean,
so that's so in other words, seeing what we did is like there's some sort of correlation between there, but it's not causality in the true sense of the word. I mean, like you would, what I call true causality, because you have to have a lot of other things. Call something a real cause.
Not the Bradford Hill criteria.
So how do you handle when the time intervals are not the same, are different?
Well, there's methodology to do that. It's a little more complicated, but it can be done. That'd be another technique. So how many of these are collected?
There's a lot of things.
So, I would say there's a lot of things in time series that you can do. Like we don't necessarily need to have time series that are stable. You probably, if you watch the cable market TV shows, you probably heard the term market volatility. Well, we can do time series, but we can do volatile time series analysis. There's a lot here, but this was just kind of the basic idea of time series, and I think the more useful ways the more useful ways of applying time series.
All right, terrific, thank you.
Thank you.